Okay, so today we're going to just continue this discussion of dual vector spaces. So till now we've defined the idea of a vector space on a manifold. So manifold naturally comes equipped with the vector space which we at every point P. Okay, you have a vector space which we denote as TPM. Okay, and that space is just defined by differential operators, directional derivatives essentially at the point P. Okay, now for any vector space, this is not just true for vector spaces on a manifold. For any vector space, it's always possible to define a dual vector space. Okay, you've seen, for example, this in the context of quantum mechanics with Hilbert spaces. So this dual vector space is denoted as TP star M. Okay, and this is called the cotangent space as opposed to the tangent space, which is the space of vectors. And what we say is, okay, if there is a vector omega which belongs to this dual vector space TP star M and a vector V which belongs to TPM, then we define an operation. Okay, the operation is the dual vector acts on the vector V, okay, and gives you an inner product which belongs to real numbers. Okay, and what we'll do is we'll define some. So this is a real vector space as opposed to the complex vector space of quantum mechanics, where the result of this inner product can be a complex number. Okay, so what we do is we'll define some dual vector, okay, omega, which belongs to this this dual vector space. And the way we will define it is by first defining what the inner product should give us for this vector. Okay, and we will define the dual vector in terms of a particular function f, which is some smooth function on the manifold M. That is, f belongs to a space of smooth functions on the manifold. Okay, which we previously denoted as capital F of M. And what we do is we denote a vector omega which depends on f as df. Okay, and this is our specific choice for a dual vector. So it's a dual vector defined in terms of some vector f. So this d should not be thought of as differentiating the function, although there is a reason why we write it as d times f. Okay, but for the moment you just think of this entire symbol d times df as the dual vector. Okay, and it just belongs to this dual vector space. So don't think of it as a differential of this function, because there's no such notion. Okay, so at the moment df is just a symbol and we will give it a meaning now. Okay, so what we do is we say that if the vector v belongs to the tangent space at the point P, so that is, you can write it in, let's say, in coordinate notation as v mu partial x mu. Okay, where you have some coordinates x mu on that patch. Okay, which describe the coordinates of a point P. Now what you can do is you can define the inner product of this dual vector df with v, or the action of the dual vector on this vector v as this inner product. And by definition, we choose this inner product of df to be v mu times partial f partial x mu. Okay, evaluated at the point P. Okay, or at the point x mu of P. Okay, and this belongs to real numbers. Okay. And what this does is it gives us a prescription for how to pick a particular dual vector at every point on the coordinate patch. Okay, so at every point in the coordinate patch, we can pick a dual vector from the space of dual vectors TP star M, such that it satisfies this property that given a vector v, okay, we are picking and a smooth function f on the manifold, we are picking the dual vector at the point P, which gives us this, the result of the inner product, or the action of df on V gives us this. Okay, it's basically V acting on f, okay, which is a real number. Okay, V acting on f at the point P. Okay, so this is the directional derivative in the direction of the vector V acting on the function f. Okay, and if you evaluate at a point, it gives you a number. So and the other thing is, if you write it like this as v of f, you can see that it's clearly coordinate independent. So although in particular coordinates you can write it like this, this definition, okay, it makes it clear that this is a coordinate independent definition of what the dual vector is. Okay, so this is how we define, this is how we're defining the meaning of this dual vector df. Okay, So now let's take a specific example. Okay, so let's take the smooth function on the manifold, at least within our, so this is, sorry, let me just draw the manifold. So let me draw the manifold. This is a coordinate patch. Okay, and we'll define a smooth function, at least its definition on this patch is smooth, and we can extend it to the rest of the manifold. But within this patch, we say that this function is just x nu. That is, it returns a particular coordinate of a point. Okay, so that if I take the point P, I find the coordinates of this point P. Okay, that is, I find the coordinates in Rn. And I take the newth component of the coordinates. Okay, so if nu is 1, then I will take the x1 coordinate. Okay, if nu is 2, I'll take the x2 coordinate and so on. And that is clearly a smooth function on this patch. Okay, so you take f is equal to x nu. That is, you take coordinate functions. And you take the vector v, okay, to just be directly one of the basis vectors. That is, you take it to be partial x mu. Okay, that is, we've taken v mu at the point P. Okay, we've taken v mu to be 1 if, sorry, okay, let's call it v nu. 1 if nu is equal to mu, 0 otherwise. Okay, so for particular mu, okay, this is non-zero. And for that particular mu, the vector v is in general this, okay, and in particular, it's just going to give you this. Okay, partial x mu. You're picking out one particular direction, okay, one particular coordinate basis vector. Okay, and now what we're going to do is we're going to say, let us ask what is df, okay, for this particular f, that is f is equal to x nu, acting on this particular vector v, okay, where this particular vector v is partial x mu. Okay, so let's work out this particular case. So what we're doing is essentially we're saying, so I'm just plugging in for f as x nu and writing it as dx nu. I'm plugging in for v as partial x mu and writing that over here. And now we'll use the definition of what we mean by the symbol, or what its action should be on the vector v. The action on the vector v should be such that it yields the action of v on f. Okay, so in other words, it's going to yield partial x mu acting on x nu. Okay, which is going to be just delta mu nu. Okay, delta nu mu. Okay, so if mu is the same as nu, you get 1. If mu is different from nu, you get 0. Okay, so now you can think of this dx nu. Okay, so dx nu is some space in the dual, some dual vector, and you can think of dx nu's now for every value of nu is 1 through n, as being a dual basis. Okay, for the cotangent space. Okay, so just like you have these basis vectors for the vector space, okay, for the dual vector space, you have these vectors which we denote as dx mu. Okay, so these are a basis of TP star M. This is a basis of the tangent space at M. Okay, and this is the basis of the dual or cotangent space. So since the basis is the same dimension, so the dimension of the vector space at M, sorry, the dimension of the dual vector space at M is the same as the dimension of the vector space at M, which is the same as the dimension of the manifold, okay, where the manifold is such that it's locally homeomorphic to Rn, and this is equal to some n. Okay, so all of these have the same dimension. Okay, the dimension, so but this is a dimension of a vector space. This is a dimension of a manifold. These are very different things, but those dimensions are the same. Okay. So any arbitrary element of TP star M, okay, that is any element of the dual vector space, can therefore be written in terms of this dual basis, okay, using some vector coefficients times the basis vectors. Okay, so once you have a set of basis vectors, I just need to define, so I have n basis vectors and I have n coefficients over here. So there's an implicit summation over mu included. And so these omega mu are basis coefficients. Okay, so the placement of the indices is very important. Okay, in the basis of vectors, we use an upper index mu on the partial x mu. On this basis of TP star M, we use an upper index mu on dx mu. This is just a convention, but we'll stick with this convention. Okay, and therefore the vector coefficients are such that it's omega partial mu. Okay, we write the vector coefficients, sorry, the dual vector coefficients with the lower mu, and vector coefficients we write with an upper mu. Okay. Okay. So now in particular, suppose you have some general function f, okay, and you find the dual vector df. Now df in particular is a vector in the dual vector space. So that means that there should be an expansion of df in terms of some basis coefficients times the basis of the dual vector space, okay, dx mu. So what we want to do is find what are these basis coefficients omega mu, okay, for this dual vector df. So so what we'll do is we'll take this inner product df acting on partial x mu, okay, and this is easy to see, okay. Again the action is just v on f, where this is v. So this is just going to be partial f partial x mu, okay, it's just going to be this. But if we've written df in terms of some coefficients times dx nu, okay, then what we're saying is these coefficients times dx nu acting on partial x mu, that and this action, okay, is this action of the inner product is always defined to be linear, okay, which means that I can split up this action of this inner product of these two things by pulling out the coefficients. And so the summation and the coefficients are pulled outside, and then I take the inner product over dx nu partial x mu. Okay, so this is a property of the inner product that you define it to be a linear action. Okay, and so now dx nu acting on partial x mu. Okay, what is that going to give me? We already discussed this, right?
Delta nu mu.
Yeah, this is delta nu mu. Okay, and so now delta nu mu with a c nu in front will just give you with the summation over nu, we'll just pick out c mu. Okay, so we'll pick out the muth coefficient. So now what that tells us is that these are two different ways of evaluating exactly the same inner product. Okay, df acting on partial x mu, or I can write df in terms of its basis components. Okay, c nu dx nu, and I would get the basis coefficient c mu. So what that means is that both these methods give you exactly the same result. That means that c mu is nothing but partial f partial x mu. Okay, so c mu is partial f partial x mu. So now what we can do is we can write df in terms of, now we've evaluated what these coefficients c nu are. It's just partial f partial x nu. Okay, so we can write any general dual vector df in terms of the basis vectors dx nu as partial f partial x nu times dx nu. Okay, so these are dual basis coefficients, and these are dual basis vectors. Okay, so we're not completely there yet, but you can start to see why we're using the notation df to describe dual vectors, okay, which are related to some function f. Okay, because this is starting to look like the expansion for a differential. Okay, except you have to keep in mind that the symbol dx nu means something completely different from a differential. It's just denoting a dual vector. Okay, but at least you're starting to see why this notation is starting to make sense. Okay, the reason why this is not exactly the same as your typical notion is that we still don't yet have a notion of how to think of this dual vector basis dx nu as some kind of infinitesimal distance. Okay, there's no notion of distance, right? Right now, this is just a dual vector. It's just a basis of dual vectors. That is, it's not the usual dx that you think about, which is the change in x coordinate by a small amount. Okay, this is just defined as at the point x nu, dx nu defines a dual vector. Okay, some dual vector in belonging to TP star m. Okay. 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 Now what we'll do is let's take a general omega, okay, belonging to this dual vector space TP star m, and let's take a vector v belonging to the tangent space TPM. So both of these are chosen at the same point P on the manifold, one from the vector space and one from the dual vector space. Okay, and you should be able to expand them both in terms of their basis. So omega can be expanded in terms of omega mu dx mu, and v can be expanded in terms of v mu partial x mu. Okay, so these are the coefficients of this is the coefficients of the vector. These are the coefficients of the dual vector. So now we can define the action of omega on v. Okay, and once again we can expand them in their basis, And we can use the linearity of the inner product to pull out the basis coefficients. Okay, so we can pull out the omega mu v nu, and we can write what's left inside as inner product of dx mu partial x nu. And once again, this inner product is known. Okay, it's just delta mu nu. Okay, and so what you get is omega mu v nu times delta mu nu. When you sum over mu and nu, you're just going to get omega mu v mu. Okay, so one way to think about what this inner product is, I can think about arranging the v mu's as a column vector. Okay, this is just a way to picture what is going on, v1 through vn. And I can picture the dual vector as a row vector of omega 1 through omega n. Okay, and the the dot product of these two is simply just taking the matrix product of this row vector with this column vector. Okay, and this row vector and column vector live in different spaces. This row vector describes a vector in the dual vector space. This column vector describes a vector in the vector space TP of M. Okay, and you might say that, okay, this is an n-dimensional vector space. This is also an n-dimensional vector space. So can't I mean, this looks rather silly. Why don't I just take the transpose of this and just identify these two with each other? Okay, and the answer is you could do that, and you could do that at one point on the manifold. And that would be a coordinate dependent matching of the dual vector basis with so you're matching the dual vector basis TP star M with the vector basis TPM. And you can do this at one point P. Okay, but you can't necessarily do this at all points P on the manifold in a self-consistent way. Okay, so therefore this vector space really has to be thought of as a different vector space than TPM. Okay, and if you want, you can identify them with each other. That is, there is an isomorphism between these two, but that isomorphism can only be defined at one point. At other points on the manifold, you might have to define a different isomorphism between these two. Okay, in other words, at a different point, the basis vectors are different. Okay, so this mapping becomes basis dependent, okay, between the dual vector space and the vector space. These are actually, you should think of them as two independent vector spaces which just happen to have the same dimensions. Okay. So one of the important things is the inner product is only defined between a vector and a dual vector. Okay, there's no notion of an inner product between a vector and itself. Okay, there's no notion in which we can convert this vector into a row vector and think about that inner product. Okay, so there is no inner product between vectors. There's only an inner product between either vectors and dual vectors. There's no way you can define an inner product just between two vectors or just between two dual vectors. Okay, the inner product is always between a vector and a dual vector. Okay. Okay. Okay, so now suppose you have this manifold M. Okay, and let's look at a point P here. Okay, and this point P belongs to two different coordinate charts. Let's call them U1 and U2. In coordinates U2, I will call this point, I would label this point by X. In coordinates U1, I would label this point by Y. Okay, when I say X, of course I mean X mu, the set of X mu's where mu goes from 1 through N. And Y means I use Y mu where mu goes from 1 through N. Okay, and since this is a smooth manifold, that means the functions Y of X or X of Y are well defined and differentiable, infinitely differentiable. Okay, so now this point P can be described either using the X coordinates or using the Y coordinates. Okay, so what that means is now I can write omega in terms of I can write any dual vector omega which belongs to this TP star M. I can expand it either in a dual basis which uses the X coordinates, that is, it uses a dual basis consisting of dx mu's, or equivalently, I could use a different basis which I can define as dy mu's. Okay, this is a different basis for the same vector space. Okay, so it's exactly the same dual vector space at the point P. These are two different bases, okay, for the same vector space TP star M. Okay, so the set of all dx mu and the set of all dy mu, they form two different bases, bases for all TP star M. But what that means is any particular dx mu, okay, you should be able to write it as some linear combination of the dy mu's. Okay, so what we want to do is find those coefficients, okay, of how you'd expand dx mu in terms of this alternative basis. Okay. Now we know that for any function df, okay, we can write df in terms of the basis dx mu as partial f partial x mu dx mu. Okay, that's what we already showed above. So now we just take our f, okay, to be the y coordinate, okay, some particular y coordinate, let's say y nu. So we can write dy nu as partial y nu partial x mu dx mu. Okay, and this is exactly what we were trying to do. We were trying to write dy nu in terms of the basis dx mu. The basis coefficients are, so the basis transformation coefficients are partial y nu partial x mu. Okay. And now once we do this, okay, we can figure out if I have a vector which I write as omega mu times dx mu, and I write that same vector as using a different set of basis vectors dy nu with some different coefficients omega twiddle nu. Okay, I want to know the relationship between the old basis coefficients and the new basis coefficients. Okay, because both these coefficients are describing the same vector just in a different basis. Okay, so the way to think of this is I have a row vector, okay, and this corresponds to some basis e1, e2, en. And now what I can do is I can take linear combinations of this and get some new basis. And I want to express these new basis vectors in terms of a linear combination of my old basis vectors. Okay, so what we did was we just found that transformation rule. Okay, and this transformation rule changes from one point to another on the manifold. Okay, so the relationship between the new basis vectors and the old basis vectors, that depends on where you are on the manifold, which is why I told you that even if you match the dual basis to in one coordinate system, okay, it may not match at another point on the manifold. Okay, sorry, if you match the dual basis to of TP star m with the basis of TPM, okay, that matching may not hold at different points on the manifold. Okay, okay, so now what you can do is now you can just plug in this expression for dy nu in terms of dx mu into this expression here. So you can write omega twiddle nu times partial y nu partial x mu, okay, times now instead of dy nu, I've now expanded in this basis dx mu. Okay, so now I can just match the coefficients. Since this is a basis, I can match the coefficients of any dx mu with any dx mu here. So what I will get is omega mu. Okay, so this is the expansion in the old basis, and this is the expansion coefficient in the new basis. Okay, times this this quantity here. Okay, this is my transformation rule. Okay, this is my transformation rule that takes me from my y basis coefficients to my x basis coefficients. Okay, or I can write this as I could have done the transformation the other way, and I would have written this as I can write the y basis coefficients in terms of the x basis coefficients. Okay, I can just interchange x and y. I can write omega twiddle nu as omega mu partial x mu partial y mu. Okay, so this is the transformation rule for components of a dual vector. Okay, this transformation rule is different for vectors and for dual vectors. Okay, so if you recall for vectors, I'll just write it out here. So supposing I had a vector v, which we express as v mu partial x x mu, then and I want to write it in terms of some v twiddle, which is partial y mu, then v twiddle mu would be v nu times partial y mu partial x mu. Okay, so so these two transform differently. Okay, this transforms, okay, from the x. So if I want to go to the y basis, I will use partial x mu partial y nu and sum the coefficients. And if I want to go from the x basis to the y basis, I use partial y mu partial x mu, okay, and then sum. Okay, so vector coefficients and dual vector coefficients transform differently under a coordinate transformation. Okay, this is very important to remember. Okay, so I'll just write it in words: vector and dual vector coefficients, and even the basis vectors, transform differently under coordinate transformations. Okay, that is if you switch coordinates from one coordinate patch to another, okay, to describe the same point, and you want to therefore switch your dual basis vectors, then each vector is now described by a new set of basis coefficients. That transformation rule for vector coefficients is different for the transformation rule for dual vector coefficients. Okay, I'll pause here for questions. We'll do some examples later, okay, to make this clear, but we'll finish first our definitions of up to manifolds, and then we'll start doing some definitions. Sorry, some examples, and then maybe, right now these are all just definitions, so it's probably hard to get too much intuition for what is going on. Okay, so let me just recap, okay, a little bit of what we've done. Okay, so let's recall our definitions. So what is a vector? Okay, so vector V belongs to, so on a manifold, we define a vector as something belonging to the tangent space at P. And what does the vector do? Well, V takes smooth functions. So it takes a smooth function defined on the manifold, and it obtains the derivative along some curve, okay, at P. And so each vector itself is defined as some kind of directional derivative. Okay, so in coordinates, we saw that V of f is some V mu partial x mu acting on f. Okay, at x at some particular point P, or you can think of it as the coordinates of that point P. And so in a particular coordinate basis, V we can write like this. Okay, we define the operation itself as being a vector, and it satisfies all the axioms of needed for a vector space. Okay. Sorry, one additional property that I should mention: as a derivative vector, it also satisfies another important property, which is this. Okay, this is called the Leibniz rule. Okay, or you might think of it as this differentiation by parts. So this is Vf times G plus Vg times f. Okay, this property is also very important. Okay, that these vectors satisfy this property. Okay, the way we've defined them. Okay, in their action. Okay, now the transformation rule to another basis, okay, is if we have a V which we expand in this basis, some basis as V mu partial x mu, and we want to transform to another basis V mu twiddle partial y mu. Then these basis coefficients, the transformation rule is that V mu twiddle is equal to V nu partial y mu partial x nu. Okay, this is the vector transformation rule. If you want just a simple rule of thumb to remember this, just think about this definition as expanding them in basis coefficients, and just imagine that I move this y mu up here and write it as y nu. Okay, and then this V, so I can change the dummy index here. Okay, move this y nu up here, and now this becomes V mu y nu partial x nu. Okay, so just as a quick handy rule, you can imagine just moving this y over here. Okay. Similarly, for dual vectors, okay, we defined a dual vector space, which is some TP star M. And what does this dual vector do? Well, it takes so vectors took functions and give you real numbers. Okay, dual vectors take vectors as inputs and they give you real numbers. Okay, so it's a mapping from vectors to real numbers. Okay, and it's defined by omega of V is some inner product, which in coordinates, in a coordinate basis, we can write them as omega mu V nu. Okay, where we've taken the dual vector basis coordinates to be these dx mu's. And so in the dual coordinate basis, any dual vector can be expanded as some basis coefficients omega mu times dx mu in the dual coordinate basis. And there's a mapping from dual basis vectors to vector basis, the vector basis, so that this inner product is delta mu nu, okay, in a particular coordinate basis. And so omega, which I can write as omega mu dx mu or omega twiddle dx nu, now I can write as omega nu twiddle is omega mu partial x mu partial y nu. This is the dual vector transformation rule. Okay, so if you compare these two rules, that is this rule, the vector transformation rule, and the dual vector transformation rule, you'll see that the x and y appear in different places. Okay, and this is basically, now we're changing from a basis expressed in the x coordinates to a basis expressed in the y coordinates. Okay, one more thing is that again, as a rule of thumb, if you want to remember this rule for the dual vector coefficient transformation, you can think about moving this dx nu, dividing by dx nu in some sense, and writing this as omega nu twiddle is omega mu dx mu dx nu. Okay, and then just converting this to partials. And sorry, I've written this as y, so this is y nu. Okay, so so this is a quick way to remember this rule for how to transform dual vector coefficients versus vector basis coefficients. Okay. Now, one important thing is that the dual. So for any vector space, we can define a dual. Okay. So for TPM, we defined a dual as TP star M. But the question is, suppose we had started with TP star M and tried to define a dual, what would we get? Okay. And the answer is that you would get back the original basis TPM. Okay. And the way to see this is you can think about defining, okay, to define a dual vector. What we did was we defined a dual vector, let's say omega, and we took a vector v, okay. And what we did is we defined the action of the dual vector on the vector through some inner product. So similarly, we can do that. We can define here now what we want is, sorry. Yeah, so what we want is we start with a dual vector space, okay, where some omegas which belong to this dual vector space, and we choose some vectors, okay, from the dual of this dual vector space. And what we want to do is define the action of v on w. Okay, this is different from the previous thing that we tried to define, which was the action of a dual vector on a vector. We now want to define the action of a vector on a dual vector. Okay, and again, we can define it through the same inner product. Okay, we can define it as v on w is the same inner product wv. Okay, we can choose to define it this way, and this gives us, okay, so this action of v on w is the same as the previous action that we had defined of w on v. Okay, so instead of thinking of this inner product as the action of the dual vector on the vector, you can alternatively think of it as the action of the vector on the dual vector. Okay, so therefore, basically both these spaces are dual to each other, in the sense if TP star M is the dual of TPM, then TPM is also the dual of TP star M. Okay, so you can think of vectors, and instead of thinking of vectors as mapping functions, smooth functions on M to real numbers, you can now instead think of them as, instead of taking f as an input, v takes a dual vector as an input and it gives you a real number. Okay, so vectors can now be thought of as mappings from dual vector space TP star M to real numbers. Okay, so this is an alternative way to think about vectors. You can now think of them as mappings from TP star M to real numbers. Okay. Any questions at this point?
Sir,
Yeah.
So when we are saying vectors or mappings from F to R, then we have to specify a particular point, right? Like,
Yeah. Vector at a point P, okay, is a mapping from smooth functions on the manifold to R. But yeah, that's right. These vectors are at a point P. Okay, because the vector we're defining itself belongs to a particular vector space at a particular point on the manifold. Okay, this vector space is defined at a particular point on the manifold. Okay, so now what we'll do is we'll define tensors. Okay, so now we'll take our vectors and dual vectors and we'll use them to build up newer objects called tensors. Okay, and roughly speaking, okay, what we'll define the idea of, so first let's define a tensor and we'll define a notion of a tensor of type QR. Okay, so let's define what we mean by tensor of type QR. So one other way of saying type QR is Q vector-like and R dual vector-like indices. Okay, so we'll see what that means. So the idea is if you have Q vectors and if you have R dual vectors, okay, what you can do is you can these Q vectors and R dual vectors would take Q dual vectors as inputs and they would take R vectors as inputs. So each of these vectors would act on a dual vector, okay, and return a number. And each of these R dual vectors would act on vectors and return a number, okay. And what you can do is you can define a tensor product of vectors and dual vectors, okay, and that defines a notion of a tensor, okay. So, or you can define tensor products of vectors and that defines a notion of a tensor, okay. This is similar to something that you might have seen in special relativity where we define tensor products of vectors. But then we go a step further and says that tensors exist independently of whether or not you can define them as a tensor product. Okay, so what we will do instead is just to say that we define a tensor, okay, of type QR as taking in the input to this tensor is Q dual vectors and R vectors. So it maps Q dual vectors, that is, which belong to TP star M, and R vectors, which belong to TPM. Okay, so you have to feed it all of this. You have to feed it Q dual vectors, you feed it R vectors. And the result of this is this tensor acts on uh, Q dual vectors, V1 through, sorry, Q dual vectors, V1, sorry, let me denote it as W, W1 through WQ. And you feed it uh, R vectors, okay, and the result of this tensor acting on all of these, okay, these dual vectors and these vectors is a real number. Okay, that's how you define what a tensor is. Okay, so we define the tensor, okay, as belonging to a tensor space, okay, defined at the point P on the manifold M and of type QR. Okay, that is, it takes in Q dual vectors as input and R vectors as input, and it returns a number. Okay, so this tensor T, what it does is it's a map, it's a particular map which takes you from Q dual vectors. Okay, so one dual vector, another dual vector, another dual vector times R vectors. Okay, so it also takes in R vectors as input, and the result of it, the output, is a real number. Okay, that's what a tensor, that's what we define a tensor to be. Okay, and this is a tensor at a point P on a manifold M. Okay, so just like you have a vector space, you can now define a tensor, the space of tensors. Okay, now this language is a bit confusing, but a tensor, the space of all QR tensors at a point P also forms a vector space. Okay, it's a vector space in the sense that once I take a particular tensor, I have this linear property of addition of these tensors. Okay, so I can add two tensors like this. Okay, and get a third tensor in that space. Okay, so it's like a linear vector space. Okay, that's what I mean by this linear vector space, except the dimension of this vector space of QR tensors is not n. What is the dimension of QR tensors? Can any of you guess? What is the dimensions of this vector space?
Q plus R.
N times Q plus.
N times
Q plus R, where n is the dimension of the manifold.
any other guesses?
QR.
N times Q times R.
Any other guesses?
N power P or Q R.
Anyone? Okay, we'll see in a second. Okay, so so basically now what we can do is let's find a basis. Okay, for this tensor space. So we'll write it in terms of basis coefficients times all the objects that you can construct out of these tensor products that actually map Q dual vectors and R vectors, okay, to real numbers. Okay, and in other words, what we do is we take a tensor product of the vector basis, and we take a tensor product of the dual vector basis. Okay. Sorry, I need to. Yeah. So if we take Q vectors, okay, each of these will act on a particular dual vector. Okay, and it will give me, I mean, it will reduce the what is called the rank of the tensor, or all of them together when they act on a Q dual vectors will give me a number. Okay, so all of these acting on Q dual vectors and all of these acting on R vectors. Okay, that will give me a number. So so now basically I have to specify any element of the basis of this tensor space. Okay, I have to specify mu1 through mu-q, and I have to specify nu1 through nu-r. Okay, and now if I look at the coefficients, okay, so I have to specify a coefficient which is t mu1 through mu-q, nu1 through nu-r, and I have to specify these coefficients for every possible value of mu1 through mu-q and every possible value of nu1 through nu-r. Yeah, okay, so now Devashish has the right idea. Okay, which is now you see that there are n possibilities for each of these of mu1. There are n possibilities for each of these mu's. There are n possibilities for each of these nu's. Okay, so the basis that I can construct every time I change mu or nu, I get a new basis for this tensor space. So every time I change mu or nu, I'll get a new basis. So it's actually going to be n raised to the power q plus r. Okay, that's the number of choices of mu's and nu's that I can make. Okay, each one, there are q plus r indices. Each one can be chosen in n different ways. Okay, so it's n raised to q plus r is the dimension of the tensor QR. This is a vector space. Okay, the space of all tensors. Okay, at the point P is a vector space of dimension n raised to q plus r. Okay, so in particular, if I take T10, these are vectors. If I take T01, these are dual vectors. This is the space of dual vectors. So this is just TPM, and this is just TP star M. And you can see that the formula gives you n in that case, right, as it should. Okay. Okay, so now you might also want a tensor transformation rule. Okay, that is, if I change my coordinate system, okay, from x1 through xn through to y1 through yn. Okay, so that is, I make this change of coordinates. How do my tensor coefficients transform? That is this t twiddle mu1 to mu q, nu1 through nu r. How is this related to my old tensor, the original t the original t coefficients, t mu1 through mu q, nu1 through nu r. Okay, and again, you would just have the simple rule, okay, that roughly the idea is that if it's an upper index, okay, it's like a vector coefficient, and that particular index will transform like the rule for how vector coefficients transform. So it will transform as a partial y mu1, partial x mu1 prime, and I'll replace this by a mu1 prime. And similarly, all of these indices, all of these vector-like indices, okay, will transform the same way. So all the vector-like indices will have a vector-like transformation rule. Okay, and all the dual vector-like indices, okay, will have the dual vector transformation rule or dual vector-like transformation rule. Okay, but really you have to imagine that this transformation rule is a transformation rule in an n raised to p q plus r dimensional vector space. Okay, so it's a linear transformation, but it's a linear transformation in a gigantic vector space. Okay, so this is the tensor transformation law. Okay, so in this gigantic n q plus r dimensional tensor space, so if I take one of those basis coefficients, which means I pick one particular mu1, one particular mu q, one particular nu1, one particular nu q. That is one element of this tensor basis, and I want to, and then I find the coefficient of that tensor basis, and then the tensor basis element. Then I take all such coefficients, and I find a transformation rule that relates it to the coefficients, okay, in a new basis. Okay. So it's very complicated, obviously, to express this. You probably don't even want to write it all out as a column vector, okay, which is why this rule is much simpler to use. Okay, despite the fact that it looks complicated, it's actually the simplest version of the rule that you can write down. Okay. Okay, so now let's ask the question. Now that we've expressed t in a particular basis, okay. So now that we've expressed t in a particular basis, what is its action on q dual vectors and r vectors, just expressed using some coordinate notation? So in a coordinate notation, it's easy to show, for example, that if you write this omega1 as omega1 dx mu 1, okay, and omega2 is omega2 dx mu2, and so on. Okay, then this tensor, when it acts on these, will, sorry, omega1, omega mu1, omega1 mu1, omega2 mu2, and so on. Okay, so omega1 is the first dual vector that you're supplying as an input to this tensor. Omega1 is the first dual vector that you're supplying as input. Sorry, the convention that I'm using is I'm writing a lower index. But now for this omega1, I want the mu1th component of this. Okay, so that's what's written over here as omega1 mu1. And similarly, omega2 mu2, omega q mu q. Okay, so I pick out those coefficients, those particular coefficients, and I will take the tensor with entries mu1 through mu q. Okay, and this mu1 through mu q is summed over. And similarly, I will take nu1 for the vectors. I will take these indices nu1 through nu r. Okay, for the first vector that I supply as input, I will take the nu1 coefficient. For the second vector, I'll take the nu2 coefficient, and so on. And I will sum this with the tensor coefficients nu1 through nu r. Okay, so there's only one tensor. There are many dual vectors and many vectors that I'm supplying as input. And the summation over all mu's and nu's is now just going to yield a single number. Okay, so this will just be a number which belongs to real numbers. So this is exactly what we expected. The tensor acting on q dual vectors and r vectors should give me a real number. Okay, that's how we define our tensor. Okay, so I hope this idea is clear. Okay. So now we'll define the notion of fields. Okay, so now that we have this general idea of a tensor, and of course, vectors are just a specific, vectors and dual vectors are just specific examples of tensors. Okay, So where Q is 1 and R is 0, then you get vectors. If Q is 0 and R is 1, then you get dual vectors. So now what we say is, so first let's define the notion of a smooth vector field. Okay, so till now we've defined the notion of a vector field V defined at a point on the manifold. So if we have the manifold, we have a point P, we take curves through it, we define a differential operator at this point. Okay. Now, if we can assign a vector smoothly to each point of M, that is at every point P, if we can assign a vector, okay, and remember that the vector space here is TPM, and this is another point P2. Okay, so this is TP1M, this is another vector space TP2M. So these vector spaces are different. The vector space associated with the point P1 is different from the vector space associated with the point P2. In general, they actually have nothing to do with each other. Okay. However, this vector space and this vector space, from each of these, I am now going to pick a vector. Okay, so I'm going to pick a vector V1, which I'll associate with the point P1. I'll pick a vector V2, which I'll associate with the point P2. Okay. Similarly, I'm going to do this over the entire manifold. Okay, so over the entire manifold now, it's like we're picking vectors that belong to this vector space. Okay, so one simple example of picking a vector. So this is called picking a vector field. Okay, and so this is similar to in electromagnetism when you pick the electric field at all points in space, let's say, right? You're picking a vector field. Okay, strictly speaking, the electric field at one point is in a different vector space than the electric fields at other points in space. Okay, so so you're using sort of the fact that I can relate the electric fields at one point to electric fields at another point by sort of imagining that I can move one electric field forward and compare it with another electric field vector. Okay, at the moment we don't have any such notion of how to move this this vector to another point, this vector at P1 to another point P2. Okay, so we don't yet have such a notion of how to move a vector from one point to another. In fact, on a manifold, there are many different ways in which you can move a vector from one point to another. So there's no direct way to compare this vector with this vector. Okay, so at the moment, we will just say that that at each point you just pick a different vector. But now we'll define a notion of what is called smoothness of assigning this vector. Okay, so if you recall a definition of a smooth function, not a smooth vector. Okay. A smooth function was one which was defined such that, okay, sorry, I won't recap the definition. So if we had this notion of smooth functions, okay, functions belonging to Fm, okay, and for any smooth function f, okay, you say that your vector field, okay, V, which is a vector field now, which means when I use the symbol V as opposed to VP, this is vectors at all points P. There's one vector that I picked out from each vector space at all points on the manifold. Now what we say is if V acting on F, okay, so V acting on F at one point on the manifold, this gives me a real number, right? It's the derivative at that point. It's the directional derivative of F at that point. But now if I take V at all points in the manifold, this is a vector field acting on F. Okay, this gives me at every point on the manifold, it will give me a number. Okay, so it will give me a real number for every P. And therefore, this is a function on the manifold, okay, because it takes the manifold and at every point on the manifold, it returns a real number. Okay. So now V of F is a function, and if this function is a smooth function, okay, if V acting on F is a smooth function, if F is a smooth function and V acting on F is a smooth function, then we say that V is a vector field and V is a smooth vector field. Okay, so Nakahara defines vector fields as only smooth vector fields and doesn't talk about other kinds of vector fields. So if V of F is a smooth function, then you say that V is a smooth vector field. Okay. So what does it mean in terms of, so this notion of smoothness, okay, again has nothing to do with any particular choice of coordinates, okay, but you can define this choice of, you can define this notion of smoothness using coordinates also. So within some particular coordinate patch, you can look at a point P you have a tangent vector space from which you pick one particular vector, that is your vector v at the point P. Okay, this coordinate patch, so this point P lies within some region U, which is mapped to coordinates. And so in components, I can write this V as having components V mu at X. Okay, and the claim is that these coefficients, these vector coefficients, these coefficients are smooth. That is, they're infinitely differentiable. Okay, these are infinitely differentiable functions for any choice of mu. Okay, for any choice of mu, these components of VP are infinitely differentiable functions. If they are, then V is a smooth vector field, at least within this patch. Okay, and then if it's true over all patches, then V is a smooth vector field over the entire manifold. So now the set of smooth vector fields on the entire manifold, we denote that as chi of M. Okay, so this is all possible smooth vector fields that you can put on the manifold. Okay, so now similarly to the notion of a smooth vector field, you can define the notion of tensor fields, smooth tensor fields. So the space of tensor fields on the manifold is denoted as TQRM. So rather than being associated with a single point P, these are now associated with the entire manifold. So there's a tensor space at every point on the manifold. Okay, and oh, sorry, something is missing. Yeah, so if I use the symbol, okay, so let me just some notation. So if I use the symbol tau or curly T, okay, then this curly symbol means the set of all tensor fields. Okay, the set of all possible tensor fields that you can have. Okay, so for example, a vector field, let's say, is something like this. This is one vector field. This is another vector field. Okay, and for the same points, I'm defining different vectors. Okay, the set of all such vector fields or a set of all such tensor fields is denoted using a curly T. If we use a capital T, okay, like a regular T, that means a particular single tensor. Okay, from this entire set of possible tensors, we're choosing one vector field, okay, or one tensor field. Okay, this is a single tensor field from this set. And now if we take TQR and we take say comma P, that means that we're evaluating this tensor field at a particular point. That is, we're taking the tensor at a particular point P. Okay, this is the above tensor field evaluated at a particular point P. Okay, so it's just good to keep this notation clear, because it just helps to separate the difference between the entire tensor space, a particular tensor field, and a tensor at a particular point on the manifold. Okay. So the most important thing is the tangent space, the cotangent space, or these tensor spaces at any point P. These are different from those space from the tangent space, the cotangent space, and the tensor space at a different point P prime. Okay, so the tangent space that we define here is TPM. The tangent space at another point is TP prime M. These are different tangent spaces. Okay, so you don't have a direct way to compare between these two. So there's no obvious way to compare vectors in these two different tangent spaces. Okay, later we'll see that we'll develop a notion of how to compare them, but that comparison cannot be done in general at the level of a manifold. You have to go to a metric space. Okay, so that's what we're going to do next. Any questions here? Okay, so now we'll move on to the idea of metric spaces. Okay, and so this discussion, so at least we'll follow initially for chapter 7 of Nakahara. Okay, so this is where we're going to make a jump. Okay, so I told you about the idea. So we started, let's recap where we are so far. Okay, so we started with this notion of topological spaces. Okay, so this is the most general idea in mathematics and the most abstract way to think about a space. where you only think about the points in the space and you think about neighborhoods of points. Okay, and in some sense, we thought of a circle is different from a line or an open line segment because they're topologically different. Okay, and it sort of has to do with how these points fall into different neighborhoods of each other. And topology is all about this notion of continuity. Okay. Then we went one step further and we defined the notion of a manifold. Okay, so a manifold is you start with a topological space, but then you give it additional structure. What is this additional structure? You equip it with charts. Okay, so you take a topological space, but now you also say that it has charts. Okay, charts which cover the manifold, which are open subsets, and these charts basically can be mapped to real numbers. Okay, or Rn. Okay. And when you can do this, that means that you can put coordinates on this manifold. And so now and the smoothness of these charts guarantees that you can start doing things like calculus. Okay, so we saw that you can define a notion of differentiation. You can define vector fields, which give you a notion of differentiation. All of that comes from this fact that your charts are smooth, are smoothly connected. Okay, so the smoothness of the charts guarantees that you can do things like differentiation. We haven't seen other things, but you can also do things like integration on these manifolds. Okay, and you can define things like vectors and tensors and so on. Okay, so this was so far how far we've gotten by adding additional structure to a topological space. Okay, what is the additional structure? We add charts to this topological space. Okay, now we're going to go one step further. Okay, so we have topological space plus charts. So that's a manifold. But now we'll add some additional structure to this manifold. Okay, and this additional structure on the manifold, okay, will be important when we try to define distances in this space. Okay, at the moment, there is no notion of distance between any 2 points on a manifold. Okay, because you can use any set of coordinates, and in no set of coordinates do you have a way to no set of coordinates is the preferred set. So there's no natural notion of which coordinates to use and how to define a distance on this manifold. Okay, what we'll see is that we will define a notion of a metric on a manifold. So this is like an additional structure that we impose. So we'll define the notion of a metric. The metric will be a rank. The metric will be a particular tensor. Okay, which is of type 0, 2, okay, on the manifold M. So if you have a tensor field, okay, so this is a tensor field. This is not defined at one point, it's defined at all points in the manifold, and it's of type 0, 2. What does that mean? It takes 2 vectors as input and returns a real number. Okay, so a tensor of this type, denoted as G, takes 2 vectors, U, V, and the result is a real number. And we defined it as a tensor field. Okay, so this G exists at all points P on the manifold. And what we'll see is that once you have such a tensor, okay, once you have such a tensor of type 0, 2, a tensor field of type 0, 2 on the manifold, this will allow you to define dot products of 4 vectors. And by using something like this, okay, that is now I can take 2 vectors as input and get a real number. I don't have to take a vector and a dual vector. I can really take 2 vectors as inputs and take their dot product by using this metric, okay, which is a 0, 2 tensor. And once I can take dot products of 4 vectors, you can also start to measure distances on the manifold. Okay, so now you can actually have a notion of distance between 2 points on a manifold. So the manifold plus this additional tensor field G, okay, which is of type 0, 2, a particular tensor field of type 0, 2. Okay, and the space of tensors exists on this manifold. But now you're saying, let me pick out a particular tensor field. Okay, that is called the metric. Once you have such a metric, then your space now has it's called a metric because metric means to measure. Okay, so it's kind of some measure of dot products of 4 vectors, which is in some sense a measure of the magnitude of a 4 vector, or it's a measure of distance between 2 points on a manifold. Okay, so what we're going to do is formalize these ideas. Okay, so let's look at some intuition first. So let's look at the example of a 2-sphere, okay, that we had done earlier. And let's take a coordinate patch which doesn't include the North Pole. Okay, so as we've seen earlier, you could use polar coordinates on this two sphere. You can use theta phi coordinates. Okay, and you can describe any point on this two sphere minus the North Pole using, or maybe minus the South Pole as well. Okay, using this theta phi coordinates. Okay, so you can use that. Okay, and you get a coordinate patch. Now we saw that there's this notion of stereographic projection. Okay, so stereographic projection means you take a line from the North Pole. Okay, so you imagine this entire thing is now embedded in R3. And you imagine that this is sitting on a plane, an infinite plane. Okay, and now what you do is you take a point. If I want the coordinates of this point theta phi, another way to get those coordinates is to describe them by drawing a line from the North Pole through this point onto this plane. Okay, and so now this point is labeled by these xy coordinates, and this xy coordinate is unique for this point. Okay, and so instead of using standard polar coordinates and defining the points by their theta phi, I can define them using these stereographic coordinates and define them by an xy coordinate. Okay, and now both of these are perfectly valid coordinates within some coordinate patch. Okay, so this is a manifold. Okay, in the sense that there's smooth coordinates which connect. You can't cover the sphere with one coordinate patch as we've seen before, but you can cover it with maybe two or more coordinate patches. Okay, so now we can ask, okay, given just this structure, okay, without a metric, can you define a notion of distance between 2 points on this two sphere? Okay, and the answer is no, not really. You can't really define a notion of distance. Now you'd say, well, if I look at this picture, it seems like there's an obvious measure of distance, right? I know the distance, if I know the radius of the sphere, okay, if I know this radius of the sphere, and now I'm thinking of it really as being a sphere embedded in 3 dimensions, then I know the distance between 2 points between theta phi and theta plus d theta and phi plus d phi. Okay, that distance will simply be r square d theta square plus r square sine square theta d phi square. Okay, this will be the distance between 2 such points on the sphere. Okay, but again, this is a choice of distance that you are getting from the fact that you have embedded this manifold in 3 dimensions. And in 3 dimensions, the distance between 2 points x, y, z and x prime, y prime, z prime is, we are assuming, is Euclidean. Okay, that is, the distance looks like this. Okay, if I just look at the sphere itself, it's not obvious how to measure distances. Okay, how to measure this distance. Okay, one way to see this is look at the stereographic projection. Okay, if I look at the stereographic projection, as I start projecting points which are closer, okay, to the North Pole, these points are basically going to move very far away. Okay, so the points, 2 points which are closer to the North Pole but subtend the same angle d theta, okay, versus 2 points which are closer to the South Pole which subtend the same angle d theta. In stereographic coordinates, these points are closer, but these points will actually be very far away. Okay, as I get closer to the North Pole, these points get really, really far away. Okay, from each other. Okay, these points get really, really far away. So which means that if I use stereographic coordinates, okay, and if I take the distance measure in the plane, okay, the distance measure in the plane between these 2 points for the same angle d theta, okay, is small here versus it's large here. Okay, now all I know, if you give me a manifold, is I don't know any measure of distance. All I know is I can set coordinates, and there are many different ways to choose the coordinates. Supposing you had just given me the xy coordinates and you told me that there's an xy coordinate and there's an x plus dx and a y plus dy coordinate. Okay, one way in which I could define a distance between these two is to say dx square plus dy square is that distance. Okay, but you see that, you know, whether I choose to define it like this, okay, the coordinates as theta phi, or whether I choose to define it as xy, either choice is perfectly fine as far as the manifold goes. But this measure of distance is very different from the distance measure on the sphere. Okay, so we need to decide what is the right measure of distance between 2 points on this manifold. Okay, the manifold itself doesn't carry that information. Okay, about what is the distance between 2 points. If I unwrap this sphere and stretch it into this plane, that is also a perfectly good and valid description of that coordinate patch. Okay, I just chosen different coordinates for the points. but no one has told me what the distance is between any 2 points. Okay, that distance depends on whether I'm viewing this as accurately reflecting the distances or whether I'm viewing this picture as accurately reflecting the distances. Okay, we have no a priori way of telling, okay, which one is the right way of measuring distances. You need to introduce some measure of distance. Okay, and in fact, we could have put all kinds of other coordinates on this sphere. And for every choice of coordinates, you could have defined different distance measures. Okay, and there's no obvious, in some coordinates, there won't even be an obvious choice of what is the distance measure to use. Okay, so distance measures do not come with a manifold. Manifolds don't come with distance measures. You have to impose a distance measure as an additional property on a manifold. Is this idea clear?
Sir, also I suppose that, I mean, right now we have defined the distance. I mean, in this discussion so far, we have sort of defined the distance between theta phi and theta plus d theta phi plus d phi, but I suppose there's no good way to describe a distance between 2 points which are like widely separated. Is that also a concern?
Yeah, so we're defining infinitesimal distances, but 2 points which are widely separated. Yes, you can't define a straight line distance, okay, on this space, but you could define the distance along a curve. Okay, so if you specify the curve, I can tell you the length of this curve if I have a notion of distance, because I know the infinitesimal distance. So I just go on adding up infinitesimal distances along this curve. So infinitesimal distance plus a curve will allow you to give the distance along, a path from 2 points. Okay, and this path can be anything. It doesn't have to be the shortest path. It can be like, this a path like this, and you can define the distance along this path also.
Sir, just now you said that for a manifold doesn't by itself come with a distance measure, but we can associate a chart with a manifold, and it has the coordinates defined from x0 to xn. So isn't the distance measure dx0 square plus dx1 square up to dxn square an obvious distance measure corresponding to that chart?
It's not, right? So for example, if I give you theta phi as coordinates, the distance, what you're saying is the distance measure should be this. You can choose this as a distance measure. There's nothing wrong with this choice. But first of all, this doesn't correspond to the distance measure that you would think of normally on a sphere, right? As d theta square plus sine square theta d phi square. Why is this the right distance measure? Well, this is the right distance measure if you think about a sphere embedded in 3 dimensions. A unit sphere embedded in 3 dimensions, because as theta goes to 0, okay, for the same d phi, okay, sorry, so yeah, so okay, so you can imagine as theta goes to 0, okay, basically you're going closer to the North Pole, okay, and so now, sorry, let me just draw it like this. So this is theta. This distance is r sine theta. Okay, so 2 points which are now separated in phi, which is this direction, have a distance between them, which is r square sine square theta d phi square. Okay, so because this distance is getting smaller as I go up to the North Pole, and now I'm really thinking about this as embedded in 3 dimensions, the distance between 2 points which are separated in phi by an amount d phi, okay, for the same angle of separation in phi, as I get closer to the North Pole, those points are actually closer together. In fact, when I get to the North Pole, roughly when I get close to the North Pole, all these points at different phis are almost touching each other. Okay, but as I get to the equator, those points are very far from each other. Okay, so the notion of distance being d theta square plus d phi square is obviously wrong, right? It's really this is the right measure of distance if you think about this as embedded in 3 dimensions. But again, this is one choice that you can make. Okay, which is not consistent with embedding this sphere in this way in 3 dimensions, but it's one choice you can make. There are other choices also.
Yes, sir.
Right? So it's not obvious that it should be dx square plus dy square. And again, even that choice is only valid within a coordinate patch. Is that choice smooth as I switch from one coordinate patch to another? That's also not obvious, right? Because if I'm using coordinates x here and using coordinates y here, I can maybe define the distance measure as this within one patch. And in this patch, I can define it as dy1 square plus dy2 square plus dyn square. But are these definitions consistent in the overlap? That's also not obvious. Right? For example, this is obviously wrong. Let's say if I mean, okay, sorry, but in the case of the sphere, for example, this would be wrong, right? If you actually had this distance measure, right? You can't just arbitrarily impose this in any coordinate system, right? So in the case of a sphere, see, the obvious reasoning is I can take 2 overlapping coordinate patches, right? And basically, I'm describing the same space using 2 different sets of coordinates. For example, they could be polar coordinates and Cartesian coordinates. And what you're suggesting is whether or not I use polar coordinates or Cartesian coordinates, I always define the distance measure to be this. That obviously cannot be right. Right? So we don't know. All we know is that there is a set of smooth coordinates. What is the preferred measure of distance? We don't know yet. Okay, so the manifold doesn't have such a notion with it.
Sir.
Yeah.
But we could choose one coordinate space where we define the square sum norm, and then pick different norms in the other coordinate spaces so that it's consistent with the norm in the one coordinate space we have chosen.
Yeah. Okay. Again, the important thing will be, so suppose you choose it. Okay. You can certainly choose it. Okay. So what you said is right. So if I have a manifold M, in one patch, you can make that choice. Okay. So dx1 square plus dx2 square. And you choose a particular coordinate system for which this is true. Okay. So in a particular coordinate system, this is what is true. But now, if this patch doesn't cover the entire manifold, okay, then there's and suppose it cannot be extended to cover the entire manifold. For example, if the manifold is not, the topological space is not isomorphic to Rn, you can't, like as we've seen with the sphere, you can't cover the entire space with one chart. So now if I have another chart, and by necessity I must have another chart, okay, because of topological reasons, then in this other space, I'm saying that the coordinates are this. Okay, and you're imposing this. Are these two consistent with each other in the overlap region? That's not obvious. Okay, for an arbitrary choice of coordinates, it's not obvious that you can do this.
Okay, sir.
Okay, because what you're saying is that if I change coordinates from x1 to x2, then this should be true, but it's not obvious that that is going to be true in the overlap region. Sorry, from x's to y's. Okay. Okay. So now. So we've seen that a manifold doesn't come equipped with a measure of distance. Okay, so there's no notion of distance that is like natural or best for a manifold, right? You can choose to impose one, but the manifold itself doesn't come with a notion of distance. Okay, so what you can do is you can equip a manifold with a way to measure distances. Okay, so you can give some additional property to the manifold such that you can measure distances. And this additional property is the metric, okay, which is the 0-2 tensor field, as I mentioned before. We'll see how that works. Okay, so if you have a manifold M, okay, and you have a vector x, okay, at a point P. Okay, so you have some vector x at a point P. So this x at point P we can expand in some basis as x mu partial x mu. Okay, now this x mu. Okay, let me write it using Okay, so now this is slight overload of symbols. Previously we were using dx mu for dual basis vectors. Okay, and now we will use dx mu to represent a small size of this x mu. Okay, it's just a small, some small number. Okay, so it's just the so I'm just writing the coefficient of this vector x mu as some dx mu just to indicate that this is some small number. Okay, this note, what I'm using here is in the usual sense of thinking about dx mu as a small change in coordinate. Okay, at the moment, again, we've not made that comparison, but this symbol is different from the dx mu symbol that we're using for dual basis vectors. Okay, all of these ideas are related, but we've not shown the relation yet. So for the moment, just think of this as something separate. Okay, so I've just rewritten this x mu as some small dx mu. Okay, just think of it as a small number. Okay, the coefficient of this vector is some small number. Now, one important thing that I'm not going to work out, okay, at least in these classes, is that although these vectors xp, okay, they live in a tangent space which is defined at a point P. Okay, they live at this particular point P. We can actually think of these vectors x, okay, as generating a diffeomorphism. Okay, a diffeomorphism from the manifold to itself. That is, you think about the manifold, you think about a copy of the manifold, you think about this point P, and you think about the vector xp. Okay, and you can roughly think about this vector xp, although it lives in a tangent space which is not on the manifold. Okay, it's a tangent space. Okay, you can think about, there is a way to think about, which we are not shown. There's a way to think about the notion of transporting the point P using the vector xp. Okay, so transporting P using the vector xp. Okay, and what that does is it transports, you can think of this transporting as a map from the manifold to itself. So it takes the point P to a point Q. Okay, so if I have a smooth vector field X over the manifold, this smooth vector field will define a vector at every point on the manifold. And what it will do is it will push points from one place to another. Okay, and it will basically give you back the same manifold, okay, under that transformation. Okay, so it's kind of like, let's say, like a translation of points or moving them forward or in any arbitrary way, like some points might move like this, some points might move like this, and so on. Okay, along some vector. So the vector xp at some point tells you the vector xp at some point gives you a direction in which the point P will move along the manifold. Okay, and it gives you an amount of displacement in terms of how much the coordinate of x of the point P will change. Okay, so it will take you from some point P to some point Q. Okay, x mu plus with coordinates x mu plus dx mu. Okay, so you can show this. We are not formally showing this, that this vector x mu with this coefficient dx mu, okay, will formally move the point P with coordinates x mu to a point Q with coordinates dx mu. Okay, you can think of this motion. You can think of it as some kind of flow. Okay, where these arrows, which are the vector field, represent sort of velocity vectors. And as I flow from initial time to final time, okay, all the particles which are points on the manifold will end up at slightly different points on the manifold. Okay, but the entire manifold will be mapped back to itself. Okay, all these points will come to some other point on the same manifold. Okay, so so the vector, this vector x, okay, or the set of all vectors at all points can be thought of as generating a flow. And in particular, if you take the vector at P, you can think of it as generating a flow at P, which moves the point P to some other point Q. Okay, so this entire discussion is non-rigorous. Okay, whatever we discuss is non-rigorous, but it can be made rigorous. Okay, I'm just not going to make it rigorous in these lectures. Okay, and therefore you can interpret this vector xp as a displacement. Okay, in the sense that it changes the with this particular coefficient dx mu, it changes the coordinate to x mu plus dx mu. Okay, so all it's doing is changing the value of the coordinate, but that doesn't tell you the distance that has changed. Okay, because we don't yet have a notion of distance. We just have a notion of coordinate and how much the coordinate has changed. Okay, and a vector x at a point, a vector xp at a point gives you such a notion of displacement. Okay, without distance. Is this idea clear? Bharat?
I wanted to ask in a sort of bounded manifold, if you're thinking about it being embedded, won't the Herible theorem be a problem if you're trying to define a constant field?
I'm not defining a constant field. XP, so this can be arbitrary. Okay, at some places on the manifold dx mu may be 0. At other places on the manifold it might be slightly larger. At some places it might be slightly smaller. This dx mu is x mu dependent.
Okay, sir.
So the Herible theorem just tells you that on a two sphere you can't have a smooth vector field that is non-zero everywhere, but it can be 0 at one point. Right, and you can still have a smooth vector field. So basically that point on the sphere will always be mapped to itself under this kind of diffeomorphism. Okay, so the flow, I can draw that flow in the sphere. So basically you imagine vectors so on a sphere you can imagine vectors like just start off small, then grow big. Okay, then start becoming small again. And basically at the North Pole they just become 0. Okay, and this gives you a perfectly smooth vector field, but it has to be 0 at one point. Okay, in fact it's not possible. So this you can't comb the hair on a sphere is essentially the statement that at some point, okay, if you have non-zero vectors, okay, you can't get a smooth vector field everywhere on the sphere. Okay, it's not possible. Okay, in the sense that if I want these vectors to point tangentially to the sphere. Okay, but you can still get a smooth vector field if at some places it's 0. Okay, so that point would come back to itself under diffeomorphism. Okay. Okay, so now that we have the notion of displacement, okay, so if I take a vector like this, okay, it generates a displacement in coordinates by an amount dxp. So now what we want to do is we want to define a notion of distance. And for that, what we'll need to do is define a dot product between two vectors. Okay, so if we have a vector like this, what we want to do is this vector generates a displacement in the x coordinate by an amount dx mu. What we'd like to do is define a norm of this vector. Okay, at the moment we don't have an idea of what it means to take this kind of inner product, right? This is an inner product between two vectors, not a vector and a dual vector, and we don't have a notion of how to take such an inner product. Okay, or more generally, it doesn't even have to be the same vector with itself. It could be the same vector with another vector at the same point, in the same vector space. Okay, so that is if I have two vectors belonging to TPM. So then how will I take their inner product? Okay, and I need to be able to do this, take this inner product at all points in the manifold to get a notion of distance. Okay, so in particular, since I can think of these vectors as generating displacements for small coefficients, I can think of them as generating displacements. Then I could also think of them as, if I could define this inner product, I could think about the distance associated with that displacement. Okay, so associated with the change of coordinates being dx mu, what is the distance that I've covered? Okay, that notion of distance or this inner product is what we need to define. Okay, and we'll define it next time. Okay, but roughly speaking, you can understand now why you need a 0-2 tensor. A 0-2 tensor takes two vectors as input. Okay, and the output is a real number. So you can use this to define an inner product. So if I have a 0-2 vector at every point on the manifold, I can now use this to define inner products of vectors. Okay, not inner products of vector and dual vector, but really inner products of vectors. And once I can define inner products of vectors, we can get a notion of distance. And since infinitesimal vectors can be thought of as displacements, you can get the notion of a distance associated with an infinitesimal displacement. Okay, so that's how this metric is going to be useful, and that's what we're going to focus on next, is this idea of adding a metric to a manifold to get a metric space. Okay. Okay, we'll stop here, and just any questions we can take.
Hello, sir.
Yeah, Tasha.
Sir, like for a manifold, we are saying that there is no notion of distance measure. That is why we are providing this metric. But this metric is a 0 to rank tensor. But a manifold comes with a tensor field. So, and it is also a tensor field.
A manifold doesn't come with a tensor field. It comes with a tensor space. Okay, which means that you can define it comes with it doesn't tell you which particular tensor to pick out, right? So the difference is between considering the space of all tensor fields of 0, 2, okay, on the manifold, versus picking a particular tensor field on the manifold. Okay, this notation that we defined earlier. It's like saying every point in space can have an electric field. Okay, the electric field can live in this space of possible electric fields at each point. Okay, this is like kind of like picking out a vector. Okay, so it's like picking out it's like saying the tensor space or the vector space of 1, 0 tensors on the manifold. Okay, if I pick out a particular electric field configuration, that is picking a particular vector at each point in space, then that is picking an element of this space, and that is T10. So this is picking a particular electric field configuration. So similarly, we're picking a particular 0-2 field configuration on the manifold. Once we pick that, that is what we call a metric.
Okay, sir, I got it.
So the manifold only comes equipped with these spaces, but it doesn't tell you which ones to pick. Yeah, Malvika?
Yes, I have like a small doubt with this. So when you define like a flow from P to Q, P and Q are basically points that belong to the same patch, right?
Yes, yes. So I assume that the transformation that I did was small enough that it's guaranteed that there will be another point in the same patch.
So if it belongs to the same patch, how does anything which okay, so we're supposedly going to define a distance from this displacement, but how can we think of this distance being something global if it's still, you know, if it's defined from distances displacements which are only in one patch?
Because the manifold is covered with such patches, right? So at every point, okay, so what you can do again is between neighbors, okay, any two neighbors, you can along some vector, okay, you can think of the displacement, and I can find the distance between these 2 points. And now if I want 2 points which are far away, I just have to follow a path, okay, and this path goes on connecting points which are close by, close by, close by, close by, close by, till I get there. And once I can define a notion between any point and some neighbor, any point and some neighbor, any point and some neighbor, I can go on adding up all those distances to get the total distance, even if this point lies in a different coordinate patch. Right, because the neighbors always lie in the same coordinate patch.
One other doubt I had is that the way we're defining distance right now, it's not unique, right? Like the way we've defined distance right now, if you keep
distance,
going from,
you mean along the curve?
Yeah, we could have a lot of different curves from between 2 points.
Yeah, so to define a notion of distance, you need a curve.
Yeah, but we've not chosen one particular curve between 2 points. We've
yeah, that's right. We've not chosen one particular. So the notion of distance is first of all defined as an infinitesimal distance. And if I want distance between two faraway points, then I need to talk about which curve I'm using to connect them. Later we'll see that once I have a metric, then I can draw many curves, and we can define the notion of shortest distance or longest distance between these 2 points by picking a particular curve which has the shortest distance in this space.
Okay, all right, sir.
So just like in Euclidean space, right, you can have many ways to get from A to B, and you can define a distance along each path. And you can define the straight line distance as the shortest distance between these two. Okay. Similarly, on a sphere, the shortest distance between 2 points will be along the longitude that connects them, but there are many other curves that can connect them. Okay, but you see on the sphere, there is the notion of straight line between 2 points in a curved space is only the notion of minimum or maximum distance between 2 points. There's no other way to define what you mean by a straight line in a curved space.
Yes.
So first you have to have a notion of distance, then you define the notion of straight line.
All right.
Okay. It looks weird because in Euclidean space, we're just so used to think of straight line as being the measure of distance. Okay, yeah, so like I said, so if any of you want and are back on campus, so things like this kind of flow, right, and these kind of ideas, which are a little more about differential geometry, these are some of the topics that I could discuss sort of in a separate discussion. They're not really necessary to build the entire context of general relativity. Okay, they do help you think about some of the more advanced material in general relativity, but they're not required for this course. Okay, so if you want to see rigorous definitions of these kind of things, those are things that I could discuss in sort of extra classes, which could be held in person. Okay, so yeah, so maybe I'll circulate a sign-up sheet for that to just see how much interest there is in having those classes. And if you're not on campus and you're still interested in at least seeing those discussions, I could maybe at least send you the notes for those discussions, which will be prepared in a similar format. Sorry, Malvika, I can't hear you.
Oh, sorry. Is it possible to hold those discussions in a hybrid format?
You mean some kind of online thing? I could see if they have some kind of AV setup. Probably, since it's an extra class and not part of the regular curriculum, might have to do it on Saturdays. So we'll do it after the midterms, and I'll see if we can get one of the AV rooms so that the lectures are recorded.
No, so I mean like a hybrid
Live?
class. Yeah, live.
I don't know how we do a live class. I mean, I'm not sure if the recording equipment. Okay, let me find out if it's possible. I mean, the simplest thing is just to put a laptop there, but I'm not sure if you'll be able to see the entire blackboard if I do that.
Alternatively, you could write things out on the tablet and then project it to a screen or something.
Okay.
I mean, that's what one of my other courses professors are doing.
Okay, yeah, I mean, if any of you others also have good suggestions for how to hold a hybrid class, I'm happy to hear it because, I mean, also I sort of see that as it defeats the purpose of a little bit of the in-person class if I'm kind of just using the tablet. But sure, I mean, we could figure out something, right? For I mean, especially for if you're interested in attending from home for these extra classes. Sorry, I'm just going to stop the recording here.